Climate change is intimate and personal. At this point, it affects you every time you go to the grocery store, or fill your gas tank, or vote, or flush the toilet, or put on your long underwear for a later than usual snowfall. And every year, it will affect you more. At the same time, it's cosmically impersonal. It involves gases and rocks and chemicals that have been operating in relationship for billions of years before there were any persons or underwear to contend with at all. In between these two levels, the sphere of your bedroom and the sheer vastness of the history of the universe, there are still other vantage points to look at climate change from. Climate change is a collective and a systemic problem, dealing not just with individuals, but with entire populations and global systems, like energy grids and international trade. So we have to kind of zoom in and zoom out, travel through time and space. And as centuries of mad scientists have taught us, it's not an easy task. Hi, I'm M. Jackson, and this is Crash Course Climate and Energy. Think about it. There's the human lifetime, where we all live, where there's weather and politics and hard choices and beautiful moments of collaboration. And then there's hundreds of years that contain full human lifetimes, the generations yet to come that will be impacted by the climate-related choices of today and yesterday. On top of that, there's the multi-billion-year timeline of Earth, which is entirely alien to our human perception. But we won the planetary lottery with our habitable Earth, the only one out of the thousands of planets known in our galaxy where life like ours can survive. So yes, truly understanding climate change across all these timelines is tough. Sometimes it's downright mind-blowing. But it's on us to grapple with what's happening not just to the Earth, but to all of its inhabitants, as the climate changes faster now than ever before. And I mean that. The Earth's climate has never changed this fast. Let's start at the human scale. A single human, actually. A human named Eunice Foote. In the 1850s, she was reading an issue of Scientific American and became curious. And like any good scientist, she nerded out about how the sun heats up the Earth. She wanted to see how density and the mixture of gases in the air affected how much heat the atmosphere could hold on to. And she tested that with a series of experiments. In one of them, she noticed that high concentrations of so-called carbonic acid gas made the air heat up faster and stay warmer for longer. Based on her experiments, she concluded that if the atmosphere ever contained more of this gas, then we might also expect the global temperature to be higher. Today, we know carbonic acid gas as carbon dioxide. So Foote became one of the first scientists to make the link between carbon dioxide and atmospheric heating. It was one of the first experiments demonstrating the greenhouse effect. You know that wash of warm air you get when you go into a greenhouse? It happens because glass panels do a great job of trapping the sun's heat to nurture your tomato plants. Well, imagine scaling that up to the entire Earth. But instead of glass trapping heat, it's gas. Specifically, gases like carbon dioxide, methane, and water vapor, which are known collectively as greenhouse gases. You can think of the greenhouse effect like a giant volleyball game between the sun and the surface of the Earth, where the atmosphere is the net. And instead of one ball, there are trillions. The sun serves these balls as different forms of radiation, what you and I might experience as visible light, UV light, or infrared radiation, which is just another fancy way to say heat. Some of that radiation makes it over the metaphorical net. It passes through the atmosphere and hits the planet's surface. A lot of that energy is then absorbed by the land and the sea. Hey, where'd my ball go? The land and sea naturally reflect back some of their heat energy. But with the greenhouse effect, more and more heat energy is getting trapped by the net. Then, the energy gets absorbed by the atmosphere instead of escaping into space, the other side of the court. That causes the energy to bounce back down towards the surface of the Earth, warming it up. The Earth is losing the cosmic volleyball game, returning fewer and fewer of the sun's serves every year as the amount of greenhouse gases goes up. Now, instead of having a constant number of balls on our side of the court, we have more each day. Although greenhouse gases only make up a small portion of the atmosphere, they play a major role in controlling our planet's overall temperature and its climate. Even increasing the amount of carbon dioxide in the atmosphere by just a few parts per million can lead to temperature changes that fuel severe weather, melt ice caps, and make life on Earth generally more difficult. How do we know this? By studying the chemistry of rocks and fossils that are hundreds of millions of years old. Scientists can piece together how ancient temperatures fluctuated and how, in parallel, the composition of our atmosphere fluctuated. But if we want a more recent picture, we can get an even better record from, drumroll, glaciers. Ice cores from Greenland and Antarctic ice caps have preserved tiny bubbles of our actual atmosphere from hundreds of thousands of years ago that today scientists like me can study. What all these records tell us is that throughout Earth's 4.5 billion birthdays, at times it's been a lot colder than today, and at other times, it's been a lot warmer. And guess what is one of the most consistent variables that leads to that temperature fluctuation? You got it. The amount of greenhouse gases in the atmosphere. So let's travel through time and space to see what things look like when those bubbles were in their prime. Let's go to the thought bubble. Back when Earth was formed about 4.5 billion years ago, it was hot. And I don't mean eating your body weight in popsicles hot. I mean covered in an ocean of molten rock hot. Earth was still being pummeled by debris from the formation of the solar system. And volcanoes were spewing out a whole lot of carbon dioxide, helping to trap all that heat. Over millions and millions of years, the molten rock solidified, forming a solid surface on the Earth. And millions of years after that, the primitive ocean formed. As a result, the Earth continued to gradually cool down. And then, a couple of times throughout its early history, before animals we'd recognize today even evolved, things got really cold. So cold that researchers think ice sheets and sea ice extended all the way to the equator. These are called snowball Earth periods. And scientists have a few ideas about why they happened, ranging from volcanic ash blocking out the sun to a drop in carbon levels, which was possibly a result of things like early plants sucking in the gas for photosynthesis. After that, it got hot again a few times over the next 500 million years, most recently about 56 million years ago. Back then, average global temperatures were as high as 23 degrees Celsius. There would have been no ice at the poles, and palm trees and crocodiles could be found at the Arctic. If humans had been around, we'd probably have been building tropical water parks at the North Pole. Because if there's one thing we know for certain about our species, it's that we love a twisty slide. But maybe thankfully for everyone, modern humans wouldn't evolve for over 55 million years. We know our fragile civilizations, water parks and all, wouldn't have stood a chance for these dramatic shifts in Earth's climate. Thanks, Thought Bubble. Now, luckily for the human species, the ice core record of the last 800,000 years reveals much gentler temperature fluctuations. At least, until we get to the last 200 years. In just a couple of centuries, temperatures have gone up faster than ever seen before in recorded history. And the average temperature on Earth today is the highest it's been in 100,000 years. We've never experienced this before. Even when Earth emerged from previous ice ages, the planet warmed up at a rate of only about 1 degree Celsius per 1,000 years. But today, global temperatures have shot up by 0.7 degrees Celsius per 100 years. That's almost 10 times faster. So it changed in the last 200 years. Well, there was one big thing, the Industrial Revolution, when humans discovered we could do things a lot faster and with a lot less effort by burning fossil fuels. Fossil fuels like coal, oil, and gas provided a reliable source of heat and electricity. So when we went for them in a big way, they helped to shape our modern civilization. And that's how you ended up here, watching this video on an internet largely powered by fossil fuels. But burning these fuels comes at a cost. It releases carbon dioxide. And as we've burned more of them to keep up with our growing population and our energy needs, our emissions have gone up as well. And that volleyball match keeps getting harder to watch. So this is what we know. The average global temperature has gone up, and carbon dioxide emissions have gone up. And we know that carbon dioxide is a heat-trapping greenhouse gas. As scientists have put those things together, it's led them to an inescapable conclusion. Human activity has caused the Earth to warm up at an unprecedented rate. We can measure this warming with every passing month. But its global effects aren't as straightforward. There's a big difference between what scientists study as climate and what you and I experience as weather. Weather is where we live. So when you wake up in Istanbul in March and see that it's weirdly cold and also snowing, that's weather. And although it may seem at odds with a warming planet, it's happening as a result of climate shifts elsewhere on Earth. Climate deals with multi-decade, broad-scale trends in things like temperature and precipitation patterns across the globe. But since climate and weather are so closely linked, it can get complicated. For instance, scientists agree that atypical extreme weather events are more likely when the planet's climate is warmer. But that's only because there's more heat trapped in the oceans and atmosphere to power these weather events. Meteorologists are constantly working to improve their forecasting models for both short-term weather and long-term climate, based on how much energy is in the atmosphere. By comparing and refining their models, scientists can now reliably predict some general outcomes if the current pace of climate change continues. And it might come as no surprise that it's not looking good. We can expect, and are currently already seeing in some cases, melting ice caps, rising sea levels, shifts in agricultural productivity, more storms, more floods, more droughts. Basically, climate change amplifies any weather you might typically experience. And these effects can ultimately lead to global economic losses, displacement of vulnerable communities, and almost inevitably, geopolitical tensions. Changing climate and changing weather patterns will have a significant impact on everyone, all over the globe. But not everyone will experience the same consequences of those impacts, or be able to adapt to them in the same way. And those who have been and may continue to face some of the most severe consequences are often in regions least responsible for the greenhouse gas emissions driving global climate change. So the question becomes, what do we owe each other as roommates on this singularly lucky planet, where we live alongside tomato plants and vibrant blue glaciers and frill-necked lizards and blobfishes and incredible human creativity? We know temperatures have fluctuated dramatically over Earth's long history. But by burning so many fossil fuels and flooding the atmosphere with gases like carbon dioxide, we also know we're causing temperatures to rise faster than ever. And while this is a massive challenge that won't have easy solutions, there are lots of fascinating ideas for how humans might tackle climate change from a number of different directions. We don't know all the answers, and we can never return to the Earth of 250 years ago. But we'll explore the many cobblestones that might make a pathway forward towards a new way of living together on our Earth, even if it's a bit bumpy. Special thanks to Steven Saar, our volleyball coach for this episode. Steven, thanks for never spiking the ball at our face, except for that one time, and for being a Patreon supporter. Crash Course Climate and Energy is produced by Complexly, with support provided by Breakthrough Energy and Gates Ventures. This episode was filmed at Castle Garrity Studio and was made with the help of these nice people. If you want to help keep Crash Course free for everyone, forever, you can join our community on Patreon.